Without any further ado, I'd like to introduce our first session today, Abusing Scripts in Apps on macOS by Thomas Reed. Hello, Thomas. How are you?
Hey, good. How are you?
Excellent. If you'd like to share your slides, we can go ahead and send you live here.
Let's see. I think I have to request control. All right, I requested control, just waiting for the ability to share.
We'll stop our content share here. There you go. Go ahead and try it.
There we go.
There we go. All right, we see your slides.
Seeing my slides? Perfect.
And you're live. You're good to go. Thank you, Thomas.
All right, thank you. So today we're going to be talking about abusing apps in scripts on macOS. Little bit about myself first. Obviously, you've already got the intro. I'm Thomas Reed. I work for Malwarebytes, and I do a lot of the Mac threat research here at Malwarebytes. So first things first, we're going to just do a brief little introduction to app bundles on macOS. Most of you probably already are familiar with this, so I'm going to go over this fairly quickly. So as many of you should already know, Mac apps are really a folder with a very specific structure called a bundle. And the executable is contained inside the subfolders content/macOS, and can have whatever name you want it to have. Commonly, that executable is a Mach-O binary, which is a native Mac binary, but it doesn't have to be. It can be a variety of different things. And what's really important to understand is there can be a lot of other executables all over the place elsewhere inside the bundle. There's some basic app info in the info.plist, no executable code. The code signature folder has some information about the code signing for the app. And the reason that I point this out is this code signature actually covers lots of different things, not just the executable in the macOS folder. And that'll be important later on in the presentation. So let's get started with an example first. So what I'm going to do is I'm going to walk through an example of attacking my own old software, Adware Medic. So if you're not familiar with Adware Medic, I know a lot of you are, but some may not be. This was an old Mac app that I wrote that was designed to remove adware from Macs. And at the time that I wrote it, I wrote it in a rapid app development environment, and formerly known as RealBasic. I don't know how to pronounce the new name, Zojo, I don't know. I'll probably just say RealBasic from here on out, and you'll know what I mean. And this app was published between September 2014 and July 15. So seemed like a lot longer than that at the time, but it really wasn't all that long, less than a year. So why am I wanting to talk about how to abuse Adware Medic? Well, for one reason, I know it very well, so I know where its flaws are. Especially in hindsight, now that I know a lot more about this sort of thing, about how to attack different apps. Now, one important reason that that an attacker might want to abuse Adware Medic is that it does authentication to root. Now, in RealBasic apps, that sort of thing, as well as a variety of other things, really are fairly limited. There's not a lot that you can do with native code to authenticate to root, or at least there wasn't at the time. I haven't looked at RealBasic in years, so maybe something's changed. But at the time, the solution for things like this was to actually bundle Apple scripts inside of your app. and use those for some of these functions. So you can see here in the diagram some examples of some scripts that were bundled inside the Adware Medic app. These are all Apple scripts, and one of those is particularly interesting, as we'll get to in just a minute. But one thing that's really important to understand is that this was a very common solution with Real Basic. Lots of developers did this. So let's go through a little video example here. So I'm just gonna start the video going, and you can see we're gonna launch Adware Medic. And if I were an attacker, I might be poking around in here trying to figure out, what might potentially be abusable. And if you choose this Take System Snapshot option, immediately you're going to notice there's a request for a password. So this is a big clue that you might be onto something that might be potentially vulnerable to an attack of some kind. So we're going to go ahead and authenticate. And what exactly, if I'm an attacker, what exactly was the reason for that password request? And if we scroll down through all this information that was gathered, you can see that it collected root cron tasks. And if you've ever looked at cron, you know that in order to get the tasks that are created for the root user, you have to have root permissions. So there's the reason that we had to have those root permissions, was just so that we could see that information. So now, how did the app actually get that information? If we look inside the app bundle, and I showed you a diagram of this on the previous slide, so you won't be very surprised by this, but there is a file in there, get.rootcrontasks.scpt. So we're going to open that up, and right here, this is very abusable. So we've got an Apple script that runs a shell script with administrator privileges. Now it's important to understand here, this script is user writable, and yet if any process goes in and makes changes to this, it will get root escalation, and that's very important. That's something that attackers look for. So what could we do? Well, we're just going to do a fairly benign example. We're just going to try and create a file using touch and see if that works. So we'll make that change to the script. We'll save the script and then go back over to Adware Medic. And we'll do the system snapshot again. And again, we're asked for a password, and when you enter it, you'll notice in the background there, you'll see it better in a second, there's the file. So that's the file that was created. So obviously the so-called malicious code in this case ran. If we take a look, we can verify that that file was created with root permissions. You can see here that the owner of the file is root. So definitely we had a root escalation there with potentially malicious code. Not really malicious in this case, but it could have been. Now obviously changing something inside the app bundle could potentially invalidate the code signature. So let's just check that and see, and you'll see that indeed that file was modified, the get root crontasks.scpt, so the code signature is invalid at this point. So what we're going to demonstrate now is if we quit Adware Medic and start it over again, you'll notice that it just starts right back up. Even though the code signature is invalid, it starts without any problems. And this will happen on every current shipping version of macOS. And I put that qualification in there, shipping versions, for a reason. We'll talk about that a little bit more later in the presentation. So just to summarize, the scripts inside the app bundle are really easy to edit. You don't need any special permission to do so. All you need to know is you need to have a basic understanding of AppleScript. And even that, really, you don't need that much. You can just append something to the shell script that one script is running. Now, different apps might have scripts that are embedded inside of the Mach-O binary or something along those lines that can make it a little bit harder to edit, but still doable. And as I pointed out, root escalation is possible, which is always a bad thing. You never ever want root escalation vulnerabilities in any of your systems. And so what, as an admin, you really need to do is you need to understand when and with what permissions scripts are being executed on your endpoints. And these applications like Adware Medic, which unfortunately was not as secure as I would like in hindsight, they can cause problems, for this sort of thing. Now, I just picked on my own app here, but you might be wondering, so, okay, this is the way that Thomas Reed did it, but maybe there aren't a lot of others that do the same thing, or maybe this is only limited to the Real Basic community. Maybe they're that community is the only one that really does this very much. So let's take a look at some other examples. So here we've got VMware Fusion, and inside the app bundle, you'll see a number of shell scripts. One of which I'm pointing out here has a comment in it that says that it must be run as root. So that's pretty juicy information. If I'm an attacker, that's really interesting to me. I wonder if I can edit that file and get root escalation. Well, fortunately, no. That file requires root permissions in order to edit. So doesn't really provide us root escalation. So let's take a look at another example. Avast has got a bunch of shell scripts inside of its app bundle as well. And again, here's one that has a comment that says that it needs root permissions. So can we abuse that potentially? Well, again, no, it needs root, so we really can't do anything interesting with that. If you've already got root permissions, it isn't really going to do you a lot of good to change one of these scripts. So let's take a look at Google Chrome. Inside the app bundle, buried very deeply down inside the bundle, there are some shell scripts. One of these in particular, the Keystone Promote Preflight script, has a comment in it that says it's called as root. So again, that's a great clue that we might want to use this for potential root escalation. And it turns out we can. That script is actually user writable. Now, I don't know the exact circumstances when that script is called. So I don't know that Chrome may have some other ways to prevent you from attacking those scripts, but it's possible you could get root escalation with this. Transmit is it's a popular FTP app, and it's got this Apple script inside of its app bundle, and it is user writable. Now, this script does not actually have the doesn't run any scripts with administrator privileges, but you could always add that to the script. And if somebody saw a sudden authentication prompt, we've seen cases in the past where an application that had never shown an authentication prompt in the past started showing one, and people were willingly entering their passwords and giving malware root permission to their systems. So it's possible. It's just not as ideal as an app where you expect to see an authentication request. BBEdit, my personal favorite text editor, also has a bunch of Apple scripts inside of it, so those could potentially be abusable. These all are used for various user-initiated activities, and they could potentially be abused, but I don't know how useful that would be. It might not be that useful. Even Hopper Disassembler, a security tool, a debugger and disassembler, has Python scripts embedded inside of it, and those could potentially be abused somehow. It would be a little bit more difficult to get the root escalation from Python, but I'm sure that there's a way. Now, you might wonder a little bit if there's no, if none of these are really giving root escalation, what's the point? And honestly, if you can't get root escalation, the only point of modifying one of these scripts would be to have some kind of a stealthy mechanism for persistence. And we have seen malware that does that sort of thing. The most infamous example was the Key Ranger ransomware years ago, which it had no method of persistence except when you opened up the infected copy of the Trojanized app that it was inside. So that's always a possibility, but it's not as powerful as actual root escalation. So we've just talked about apps, about scripts that are inside of app bundles so far, but there are a number of apps that also have scripts that are stored elsewhere on the system. So Munki is one of those. It has a directory in user local Munki. I'm sure that most of you are familiar with Munki. I actually created this presentation originally for an audience that wasn't all Mac users, so thus the explanation of what Munki is. But those scripts for Munki, fortunately, must be owned by root. So that makes it not really very abusable. If you've already got root, there's no point in going in and editing Munki scripts in order to do something malicious. You just do something malicious with your root access. So Cocktail is another app. I think it's used to be more popular than it is today, but it is still in use, and it has quite a few shell scripts inside of it. Now, again, fortunately, these shell scripts, they're located in the root library application support folder. As such, these directories are all owned by root, so not very abusable. So I found another one here. Hide My Ass Pro VPN has some scripts in the user application support folder. And so this particular script, the user init script, is user writable. You can make changes to that file, and you can get malicious code to run. There's no root escalation here, but still it's a good way to potentially have a sneaky persistence. So these are all what we talked about so far are kind of theoretical. Okay, these are things that an attacker could do. Would they actually do it? I don't know. But let's take a look at some actual real world cases where attackers have modified scripts or binaries or something along those lines in the wild. So back in 2014, we saw some adware called Conduit, and this was adware, so it a little bit less severe than true malware, where it's trying to get your data or harm you in some way. But still, adware is pretty nasty. Definitely not something you want to have on your machine. And in this case, what this variant of Conduit did is it actually appended code to the chrome.manifest file that's in Firefox. And what it did is it added a script that would load macsearch.takeover.js. And so when you would run Firefox, this would result in that Mac search takeover JavaScript automatically running as soon as you started up Firefox. And then that script actually also ran an additional script which monitored and modified pages that you loaded in Firefox. So that's pretty nasty, and it involved modifying a JavaScript file inside the Firefox bundle, which, you know, is kind of exactly what we've been talking about so far. Here's another example. There was some malware that we called ChromePatch back in 2017. And there's a file called resources.pak buried deeply inside the Chrome app bundle. And this file has all kinds of things inside of it, including some JSON that contains scripts and things like that, or settings. And you can see here on the right is the legitimate unmodified copy of resources.pak, just a small snippet from that file. And on the left is the modified copy that was changed by ChromePatch, and you can see that it set a new content security policy. And then if you look down at the background, so it changed the background from an HTML page called background.html to a script called thunk.js. And then it also modified the permissions to give the script additional permissions that it wouldn't have had before. So then another example here is Crossrider, also sometimes known as SurfBuyer, as well as a number of other names. And this was back in 2020. And this actually did something really sneaky and pretty malicious, in my opinion. What it did is it actually, when you ran the installer, it would put up a screen that would cover your entire display, and it would say that it was updating. And I forget exactly what it said that it was updating, but it said it was updating something. Meanwhile, in the background, it created a copy of the Safari app. So it would copy the copy of Safari that was on the system into private/temp. And then inside that copy of Safari, it modified the extensions preferences view.js file buried down deep inside the bundle. Now this script is actually, I don't know if it's still in current versions of Safari. At the time when you ran Safari, it would run that script automatically at startup. And so what Crossrider did is it actually made changes to that file in order to get their extension installed without user interaction. So the installer would actually pop open that copy of Safari. The screen was still obscured by their, supposed update, and so the user would see none of this. Safari would pop open in the background. It would run that script. That copy of Safari would then have the malicious Crossrider browser extension installed. Then it would quit that copy of Safari and delete it. And at this point, your Safari settings have already been changed. And so when you open up the legitimate copy of Safari, that Crossrider browser extension is going to be active. And so this was their technique to get around Apple wanting to make sure that the user consented to installing these these extensions. And here you can see in the image below that exactly what the change was. And in this case, the unmodified copy of the file is on the left. And on the right, you can see what was changed. And you can see that it's designed to enable certain extensions by name, My Coupon Smart and Any Search. And so this is a pretty nasty and sneaky way of getting that done. And if this had been malware, it could have been a lot worse. So these aren't quite exactly what we've been talking about, but they're fairly similar cases where scripts were abused in some way, or binaries were abused in some way. So in the case of ThiefQuest, aka EvilQuest, this was some malware that appeared in 2020, and it was designed to steal data. The name was changed because it turned out that there was an actual legitimate video game called EvilQuest, so the name was changed to ThiefQuest. So what this did is it actually would iterate through all the files in your user home folder and look for any Mach-O binaries that were inside there. And for any of those binaries, it would actually prepend malicious code to the beginning. And that malicious code was designed so that it would run and then it would call the legitimate code that was now located at the end of the file. And one really good example of files that it infected on lots of systems, because lots of people have Google, is Google Chrome and any other Google apps. They store a number of helper processes in the user folder with user permissions. So it was fairly trivial for ThiefQuest to modify those files. Now, the one piece of good news in this case is that Chrome was actually fairly intelligent about this, and so if you infected your a test system, for example, that had Chrome on it, and then you launched Chrome, those helper processes would immediately be reverted back to a clean state. So Google noticed they'd been modified in some way and switched them, or updated them, or changed them back to the way that they should have been. So the malicious code did not actually run, which is good. But other processes in the user folder probably not so lucky. XCodeSpy is another example where a script was used. In this case, a malicious script was added to an Xcode project. Now, in this case, it's not something where you'd have to have downloaded the malicious project to begin with. In this case, but there's nothing saying that you couldn't have some kind of malware that looks through all of your Xcode projects and injects a script into them. So basically, what it did is in Xcode, you can have you can set a project to run a script as soon as you launch, as soon as you open the project. And so in this case, what what was added was that it would run sh with and run this script here that's shown, very heavily obfuscated. And what that script would actually do when you launched the project is it would actually install an eggshell backdoor. And eggshell is it's a so-called legitimate backdoor. It's used a lot by red teamers, or it was at the time. It was used a lot by red teamers or by security researchers who were interested in experimenting with backdoor code. So it's kind of sort of legitimate, but it's also been abused for malicious purposes. So and so yeah, you just have to imagine a case where this malware modified your existing Xcode projects to add this script, and that would not be a good thing. We also see a lot of cases where you find scripts in launch agent or launch daemon plist files. And this is it's definitely possible to do. It's easy to do. You really shouldn't do it the same way that a lot of these examples do. So I'm going to show you some really weird things that we see malware doing. And although these are files that malware is dropping on the system, just imagine that malware were to change an existing launch agent on your system in some of the ways that we're going to talk about here. So here's an example from some adware from 2018 that we called FaceBump. And this malware, this adware, was actually impersonating the Facebook app. So it's honestly, this probably should have been considered malware instead of adware. But what it would do is it would create a launch agent plist file. So a user, I believe this was a user launch agent, and it would run sh to open the Facebook app. Now, here's a good question. Why? So those of you who know how launch agent and daemon plists work, they could have just put the path to the Mach-O binary inside that Facebook app in that first string parameter where bin/bin/sh is, and that would have accomplished basically the same thing. And they could have added those two arguments as additional strings. So yeah, it's kind of it's a good question. Why did they do it this way? Most likely, whoever created this was not all that familiar with Mac and really didn't understand how launch agent plists worked. So they did it this way. No real reason. But it does give you something interesting to look for, if you see launch agent or daemon plists doing this kind of thing. That's a red flag. Another example here was Darth Miner. This was a malicious piece of malware that was disguised as a cryptocurrency miner. And it actually would do some mining, but it would do it for the not for the user, but for the creator. And for persistence, it actually created this launch agent plist file that would run a Python script that would basically run a bunch of stuff through base64 decode. So this was pretty interesting, pretty obvious. If you see something like this in a launch agent plist, that's pretty suspicious too. We also saw exactly the same syntax used by another piece of malware called OSX.Badword. This was one that actually dropped its payload through a Microsoft Word macro sandbox escape. And so, this is another thing to look for if you see this kind of thing going on in a launch agent or daemon plist. Here's another example. This was CrossRider again. CrossRider has done some pretty sophisticated things at times. This was not one of those things. So In 2020, we saw that they created a launch agent plist file that contained a script, and it basically passed some base64 encoded JSON to the file that it was launching. What's really interesting is that it tried to run it using sudo from a user launch agent, which doesn't make any sense at all. That's not how that works. You can't just throw sudo into a launch agent and expect it to work. So that was kind of amusing, and another example of this use of scripts, in weird places. Here's another one, OperatorMac. This was in 2021. A lot of folks these days are calling similar things Adload. So I think Malwarebytes is one of the only companies that uses the OperatorMac name. And again, created a launch daemon plist file containing this script here. This is the same general idea as Darth Miner, but slightly different syntax. So again, it's piping a whole bunch of data into base64 to decode it, and then piping that into bash to run it. Now, again, it's kind of interesting the way that they did this. They run it with ZSH to run echo and pipe something into base64 and then pipe that into bash. It really makes you think, folks are not that familiar with how Macs work in these cases. So here's another one, OSA Miner. This was also in 2021. It created a launch agent plist file that contained this script here. So it runs OSA script to run an Apple script, to run a shell script, to run an Apple script, which just, why? It's anybody's guess why they did it this way. This is the weirdest thing I think that I've ever seen in a launch agent plist. But again, this is still the use of scripts in weird places, and definitely something worth looking for and keeping an eye out for. So, all right, I've just given you guys a whole bunch of information about how to attack a Mac system through scripts in various ways, through scripts in apps, scripts that are used by apps, or scripts that are peripheral to apps in some way. But now, what about how you protect against this sort of thing? I've just given you all the red team information, but no blue team information. So let's look at a little bit of possible mitigation. So first of all, upgrade to Ventura. So now that's in beta right now. So obviously you don't want to upgrade all your endpoints yet, but once Ventura is released, the really good thing about Ventura is that it now checks code signatures for apps on every launch, not just the first launch ever. So if you're not familiar with this, and the demo that we did with Adware Medic kind of alludes to this. When you run an app on any currently shipping version of macOS, it will check the code signature immediately. If the code signature is invalid, you're not allowed to run that app. It doesn't even give you the option. It simply tells you to move it to the trash. But then let's say that you modify an app after its first run. macOS will never, ever again check the code signature. So you can modify an app to your heart's content with as much malicious code as you want, knowing that it will always continue to run. Ventura changes that. So now you won't be able to do that. If you make a change, if you being, you know, a hacker, a malware author, make a change to an app on Ventura, it's going to be seen as invalid the next time you launch that app, and Ventura will not allow it to run. Now, one thing that's really important for those of you that will be upgrading to Ventura quickly after its release, there are some apps out there that break their own code signatures, you know, through things like strange non-standard update processes or the like. So these apps actually make changes to their own bundles, breaking their own code signatures, and they're up till now they've been perfectly okay with that because the apps will still run. So I know that Apple has been calling around to a number of developers. I know that because they actually contacted us because we had a bug in a version of a piece of our software that they found, and they wanted to make sure that we fixed that. But it's entirely possible that Apple may miss some apps. It's also possible that they may contact some developers about a problem with their app and the developer doesn't fix it in time. So just be cautious when you upgrade to Ventura because of this. You want to make sure that all of your apps do have a valid code signature, that none of them are breaking their code signature. So if you're not on Ventura, then another good mitigation is to periodically check the code signatures of the apps on your system. Now, you know, this may or may not be feasible for large organizations. You know, it's something that might work well and it might not, depending on your org. But you could just, you know, periodically run a script to, you know, go through all the apps on the system and check their code signature, and then, you know, report back which ones are not valid on, you know, don't have a valid code signature. And if you're looking at this data fairly regularly, you can see when something changes and you know, something becomes invalid that was previously valid. And that's a good tip-off that something might be going wrong. Now, if you're checking these code signatures, if you do decide to do that work and do those checks periodically, one piece of advice is that you can ignore Apple's apps. If you modify any of Apple's apps, they will instantly crash as soon as you try and run them. So you don't really have to worry about somebody modifying Apple's apps because of this, but any third-party app is potentially fair game. You also have to be aware that a lot of open source software is not signed. So that's kind of that's a danger because you know, unsigned software can be modified in any way, and there's no way you'd ever know unless you're doing constant checksums, which nobody wants to do. So if your org uses a lot of open source software, maybe you ought to consider signing some of it with your own signature. You know, that way you can verify it. And as we mentioned before, you know, some apps have been known to break their own signatures, so just be aware of that when you're doing this check. Another mitigation here is check your launchd.plists and look for any kind of suspicious behavior. You know, any kind of suspicious scripts in the plist, anything that's running from /var/root, like this example here. Nothing legit should be running from that location. Also, any launch agent or daemon plist that's running something from a hidden location. You know, and don't assume that because it's something that you had on your system that it's always going to be legit, because these are fairly easy to modify. Now, unfortunately, some legitimate apps will do some really dumb things. So you can see here, this particular app is using OSA script to run a whole sequence of script steps, all within the launch agent plist file. So that's really not a good idea. What I recommend you do, if you've got some kind of a weird launch agent plist like this in your org, what I recommend is take that script out and put it in a file, make it root root only, so only a root user can modify it, and then just call it from within the plist file, and that way it makes it a lot harder for someone to maliciously modify that script in some way. Another is if you're developing your own internal or external apps, make sure that they're signed and notarized, but have them check their own signature. So instead of just trusting macOS to do the job, because as we know, until Ventura, macOS really doesn't do that job. It does it once and then never again. So if your app checks its own signature, then that is a good mitigation. If it can warn the user, refuse to run, so that it wouldn't run the malicious code. Now, there are some gotchas there. Obviously, if somebody is going to reverse engineer your app and add code to it, then they could potentially disable this warning. But you're adding a little bit of, you're kind of raising the bar if you do this. And then if you have apps that contain some kind of an internal script, like an Apple script or shell script or something like that, just consider checking, check the code signature on the app or check the scripts themselves or something. If you have scripts that are not inside of an app that are distributed onto your endpoints, consider checking those individually, just to make sure that they're still legit, that nobody's messed with them. And definitely try to avoid any kind of root escalation. So don't have scripts that are user writable that then can get root permissions. And that is all for today. So I am open for any questions.
All right, very good. Thank you, Thomas. Our first is just a comment from Bruce Carter. Real Basic was pretty cool back in the day.
Yes, it was. I've got to say, the first version of Adware Medic, I was kind of torn between writing it in something like Real Basic or writing it in, Objective-C or Swift. I managed to write it in Real Basic in a week, less than a week. So that's the real advantage of something like Real Basic. You can really develop things fast if you know what you're doing.
Very cool.
Next question is from Anonymous. When you said that Google Chrome had a user editable file, was that admin or a non-admin user?
So generally speaking, when I'm talking about a user editable file, it's any user on the machine. Now, there could potentially be some cases where it would have to be an admin user, but not necessarily root. But most of the time, if root is not required, then any user on the machine could potentially do it.
Anonymous comments. I'm pretty sure if you copied an application to your desktop, the copy would be user editable, but that doesn't mean it will run with elevated permissions, right?
Yeah, so I think that's correct. If you make a copy, then it should be user owned rather than root owned. So then the question is, if that app does use root permissions in some way, how does it do that? and that's where the vulnerabilities come in. So if it actually doesn't use root permissions at all, you got no problem. If it uses root permissions, but it does so correctly through something like a helper, like a privileged helper process, then again, you've got no problems unless you already have root permissions. So the real problem would come in where you've got one of these apps that has scripts inside of it that can provide some kind of root escalation.
Our next question comes from Robin. Who are scripts bundled inside /applications run as usually, as the user running the application, or is the problem really that all scripts are run with root permissions, but the script may be editable by a non-root user?
That's a good question. So when you run an app, I'm going to pick on BBEdit for no particular reason. If I run BBEdit, it's got some scripts that I can run through there. When they run, they're going to be running with my permissions, so not root permissions. In order to run those scripts with root permissions, I would have to do something really weird. So for example, with the case of Adware Medic, that one script actually had the ability, it requested administrator privileges and caused that authentication prompt to show up. So that was where the problem was, is that, a script that was run originally by the user with user permissions was editable by user, authenticated for root permissions. And that's where the real problem comes in.
Okay, final question we have right now. What happens on Ventura if the machine doesn't have an internet connection when launching a third-party app?
That's a very good question. So checking the code signature does not actually require an internet connection. Checking the validity of the certificate that was used to sign it does. But just checking to make sure that the app hasn't been modified can be done without an internet connection. And then for notarization, if that's part of the question as well, if the developer did things right and stapled the notarization to their app, then that should work offline as well. That validation should work.
All right. Well, since we don't have any further questions, I'm going to go ahead and thank Tom for taking the time to deliver today's first session. We very much appreciate it.